Now let's discuss if there is a caveat over here. So yes, there is a caveat over here, and effectively what I'm doing is that I am trying to give an assessment how good did the robot perform. Now, if it was a big robot at my lab, I would have fitted my lab with so many sensors, tracking devices, CCTV cameras, which we used to track you, not these days, and high definition trackers, so as to get exact trajectory that your robot is taking, and then that would have gone into some data analysis engines, and that would have given all the trajectory and the performance calculations. Now the problem is that I'm really dealing with small robots, and they are autonomous, they are doing things, and they are taking their own decisions. So the performance analysis also, I will not do it. If I would have been responsible for performance analysis, letting the robot know how good or how bad you are, I would have anyways written down the entire program. So if you need human expertise, why not use it for writing down the program than just saying good or bad, 9 or 10? Okay, irony. They used me just to give scores to you in your different assessments. They could have done better. Yeah, but I also teach you and kind of program you. So, a human expertise should not be required. A robot should do it autonomously. So I cannot assess it up. And for the environment to assess it, I don't have those rich 3D sensors that sense how the robot is moving and do all the tracking and then giving you the performance score. So now I've got a great challenge, and my great challenge is that performance assessment should be done by the robot itself, which is not difficult. It's a computer program. Whatever computer program can do, it can do it. It's eventually a Raspberry Pi, Arduino, whatever. It's an embedded system. So performance assessment should be done by the robot itself. However, the caveat is using only onboard sensors. So reinforcement learning analogy, how do you learn how to walk? You learn how to walk because you fall down, so you know that that's not how to walk, but you know that you fall down because you feel the hurt. It's not that somebody tells you, did you realize 5 minutes ago you fell down? Start crying. So nobody else does that to you. So I can only use the onboard sensors, and my onboard sensors are which are limited in nature. And that is something that I will make sure that I only use performance assessment formulas. I only use performance assessment techniques. I only use techniques to give in a score to let a robot know how well did it run, how well did it act in the t amount of time, in the performance that it showed in the delta t amount of time, how good was it. I only use the onboard sensors. Now let's take in, now I'm coming up to the fitness function. Now I cannot be generic. I better start saying what is the robot doing, because I cannot make a generic fitness function formula. I cannot make in a generic formula that says how good the robot is. The robot needs to be given a work, and then I'll say how good the robot did that work. So let's take in a few quick examples maybe. So the first behavior that I will be taking in is, of course, what is called as the obstacle avoidance. So that's my physical robot. At any general time, I want to find out the... At any general point of time, I need to find out the fitness of a genotype. So I convert it to a phenotype, I load it over here, and I make it run for delta t amount of time. So that's the trajectory. This one appears to be bad. Why was this robot going and banging on the obstacle? That's bad, but I need a formula that can tell me that this trajectory is bad, this neural network is bad, give it bad marks. I need a formula that can do that. So let's try to write that down. So let's try to write down a formula that tells this robot that it showed bad obstacle avoidance behavior. And remember, I don't have this nice blue trajectory. Otherwise, I could have used lot of techniques. I don't have this blue trajectory. However, what I have is that the robot has a number of sonar sensors. They don't cost. So let me put many of them. So let's put 5 sonar sensors. And sonar sensors tell me what is the distance from the obstacles, and good obstacle avoidance means high distance from the obstacle. So my fitness function value for any RNNX will be in neuro evolution population pool. So I should be away from the obstacle. So I have to increase the distance from the obstacle. Now the distance from the obstacle is this sonar sensor will report some distance infinity. This will report some distance. This will report some distance. This will report some distance, and this one will report some distance infinity. So the distance from the obstacle is the one that is closest to the obstacle, which in this case happens out to be this. And this is the thing that I should be maximizing. But then we know from the potential field that it follows an inverse square law. So if I'm not very close to the obstacle, it's okay. The moment I start getting very close to the obstacle, the sensitivity increases either as inverse square law or as an exponential. So let's use the exponential over here. So I say the fitness function is given by phi dit. So this is dit is distance reported by ith sonar sensor at time t. And I'm calling it fitness, but let's say that it's a minimization problem. Or let's say that it's a maximization problem. Never mind. So distance from the distance reported from the ith sonar sensor at time t, and you can either use, I could have used either the inverse square law function, or I could use the exponential. Let us say I use the exponential, so it is e raised to power I love the exponential. So when d is very large, this term will become almost 0, and when d is very small, it's about to collide, then this term will be extremely large. In fact, it will be 1. So let's apply some weight over it. Let's say W1, and I need to, so I need to minimize this thing. I need to keep it close to 0. I don't want it high positive, which denotes a collision. So I need it as small as possible. The fitness function larger the better. So that's converting a minimization into a maximization by a minus W1 weight. W1 is the importance of this criterion, and minus is this thing. Now, of course, there are other terms that will be important. And the one thing that I can obviously think of is that let the robot just stand away from obstacles. Let's just stand away from obstacles. Now, that's a valid obstacle avoidance behavior. You're not colliding, but that's no behavior because you're not even moving. So, to call something as obstacle avoidance, you at least have to move. Not moving is not a behavior. So, I tell the objective function exactly that. So, I need to maximize the linear speed. I need to maximize the linear speed. So, let's say W2 times this thing. I need to maximize the linear speed. Otherwise, my robot will learn that it should never move when it's away from the obstacle because this thing is the smallest. So let's say put a summation over time over here. And there were multiple sonar sensors, so I should have already done a so the least distance which converts to the largest phi value. Oops. Okay, so far so good. Now so far so good. So velocity at time t. So far so good. Now what I really need to do upon is that if you are a good driver, you drive straight. You don't drive like this. So that's a obvious rule in driving. You drive straight. Wherever you need to go do, you drive straight. You don't drive like this. And that's exactly what I want the robot to learn, that yes, chopping is a bad behavior, and I already told it by the first term that you want to maximize speed. But I also want to tell it that just going like this over here as a circle is also a bad behavior. That's not obstacle avoidance. You're maximizing linear speed, you are away from the obstacle. However, that's too much zigzag. So I want to tell the robot that taking in angular turn is bad. So let's add it around over here. So W2 times omega t, the angular speed at time t, and again I need to minimize it. So I should be minimizing my angular speed. So let's write this thing up in a little fair manner. So the fitness function of the recurrent neural network X is as a genotype converted to a phenotype, is in the entire delta t time that I simulated the robot. So I loaded this X onto a robot and I let it go for delta t time. So in the entire simulation run, I say I need to maximize the linear speed. I need to minimize the angular speed. These are two obvious things. So I want the robot to drive as straight as possible, and I don't want the robot to really go and do this shake little driving. It's bad. And I want the robot to be as close as possible to the obstacles. Where this is just the inverse. So high distance, smaller penalty, small distance, high penalty, and it's a max over I. So all the robot will really do upon is, if it's far away from the obstacle, then this is nearly 0, and it'll try to take angular speed as 0 and it'll try to go as straight as possible. And let us look at that. So that's my map. These are my obstacles. So suppose I start over from here, I'm far away from the obstacles. So I'll try to have as much maximum speed as possible because there's no incentive of turning, as well as this penalty term is almost 0. However, when I come over here, then I need to learn that if I try to maximize the angular speed, you know that this term becomes very large very quick. So if I try to maximize the speed, this term will suddenly become too quick. So I don't want to maximize my linear speed, because the penalty due to this will be very large. So I will maximize my angular speed. I know it's bad, but this bad is okay because it eliminates me from this extremely bad. So that's why the angular speed will increase, and it will it's bad. Linear speed will reduce, that's bad, but it saves me from this bad. And again, over here, the angular speed will increase, the linear speed will decrease because it saves me from this bad. And then again, there's nothing, so I can travel straight. So this is what eventually will be learned automatically because of this fitness function. And that's exactly the same as the reward function of reinforcement learning. So reinforcement learning also, you at some state you take some actions and then you get some reward. The only difference between neuroevolution based reinforcement learning as a neuroevolution and a Q learning is here you're taking a series and a sequence of actions and then you're getting cumulative reward, and there you immediately keep getting the reward. So that's the difference. Of course, neuroevolution is still multi-agent and Q-learning is still single agent, and that makes a whole lot of a difference in computation time. Neuroevolution is ridiculously slow. So that's my fitness function, and it appears to be doing the correct thing. So the linear speed will increase only when it's away from the obstacle. Otherwise, I don't want to take that penalty term because of obstacle. That's very bad. So I'll never ever go near to the obstacle. That term is extremely bad, and I'll manage my linear and angular speed, minimizing the linear angular speed, maximizing the linear speeds as far as I don't hit an obstacle, because this term is honestly very bad. Now turns out that this function can also be written in the product format. So most things which are in the sum format can also be, of course, in the product format. So Vt times raised to power W1, this needs to be minimized. So minimized omega 2 W2, and it's 1 minus, so normalizing it 0 to 1, and then max I phi dit, minimizing, so 1 minus W3 and d max. So the same equation as in the format of a sum, in the format of product. You take whichever one you want. It's not that the equation has really changed. The behavior will remain the same. One you could say is in the logarithmic domain and the other one is in the sum domain. Of course, in the logarithmic scale, the products become the sum and vice versa. So that's doing something which is interesting.